Hello, I'm Mohammed Arashi, and in this session of linear model, I'm going to explain projection matrices. Before we go to projections, it is better to discuss why it is needed in linear modeling. Once again, if you remember the common notation for the linear model, uh, where y is equal to x beta, we may assume that y is n by 1, x is n by p or m, not a difference, and beta is a vector of regression parameters py1. We can obtain, of course, the estimate for one estimator for beta as x prime x, the generalized inverse x prime y. However, as we know, we have infinite number of generalized inverses. So the problem comes with a uniqueness. Can we find a unique solution for that? That's why we consider projection matrices. And with a projection matrix, you can of course find a unique solution, which we will see at the end. You can write it as a C matrix Y, which then we call this C something close to projection. We will get to that point. Okay, now let's start with projections. We have a fundamental theorem here. It says that if we are provided with a vector n by 1 of non-zero, which is a non-zero vector with non-zero elements, and we also assume D is a vector n by 1, any vector, then D can be uniquely expressed as B1 plus B2, where B1 only depends on A, which is equal to CA, and B2 is orthogonal to A, and we can find this C by this formula, and simply B2 is D minus B1. Before I go to the proof of the theorem, let's have a little bit of visualization to see what this theorem says. Let's add a page and discuss it here. Okay, here if I can just draw a line, or better say not this one, a little bit better. Let's draw this line. Let's say it's a vector A, and this is our D vector. First of all, we want to explain about the concept of projection, and projection of D onto A can be something like this. So we project it into A, or better onto A, and we say that B1, which I call it here B1, is actually the projection of D onto A. For sure, if I display minus B1, let's assume that this is minus B1, and then compute the sum this way, then this guy is actually D minus B1. So we can say that, okay, this vector here is the remaining, which is D minus B1, and we can call it B2. So if I come back to the theorem says that we can construct D as B1 plus B2. Once again, remember that here this projection we denoted by CA, and we can say, okay, of course this vector here, this vector, better say I better use another color for more visibility. Yeah, this vector, which we call it CA or B1, is actually part of the A vector, so it's proportional to A, which this proportion C can be obtained, and in the theorem we obtain it. I will come back to this theorem. So this is actually the concept of projection. We can project D onto A. This projection is actually a proportion of A, which we call it B1, so we can construct D as B1 plus D2. B2, this B1 and this B2 can construct D. Now let's back to the proof and see how we can do this. Suppose D is equal to B1 plus B2 and B1 is equal to CA plus B2. Once again, from the figure, we saw that B2 was orthogonal to A. Okay, so B2 is orthogonal to A. Therefore, if I pre-multiply D both sides with A, we have A prime D equal to A prime B1. So I can write it as A prime B1 plus A prime B2. We know that this part is equal to 0 because it's orthogonal. And also A prime B1 is equal to CA, so we can write it CA prime A. And we can easily get C as D prime A divided by A prime A, because A prime A is not equal to 0. So you can divide by A prime A. So the first part is proved. However, conversely, we can say if C is equal to this guy, then we can construct B2 as D minus B1. And then if I substitute it, then it easily follows that B2 is equal to D minus CA. And therefore, we can conclude that B is orthogonal to A, because this C is unique and B2 is also unique. So the proof is pretty simple. But the application of this theorem is very important. So for any vector D, you can do a projection to a specific vector, and then we will see that in a space that is generated by the column of a matrix, we need such a projection. Because we have columns in a matrix. Let's say we have a matrix A, and this matrix A is constructed like A1, A2, up to AM or AP, not a problem. Each of them is a vector. So I can conduct a projection on the columns, and because of that projection, we can then find a solution which we initially seek for that. Okay, once again, remember, if D is constructed by B1 plus B2, then the coefficient here, B1, C equal CA, the coefficient is given by this guy. D prime A divided by A prime A. And we call, and if this is the coefficient, we call projection of D onto A. So I will use it repeatedly in my explanations. Therefore, as I said, B1 is the projection of D on A, and B2 is component of D orthogonal to A, we saw in the visualization, and also the square length of projection. So this B1 is projection. So the square length of projection is B1 prime B1. Let me use the hand. And if I replace B1 with C A here, let's go up. Yeah. If I replace B1 with CA, so it is C2A prime A. And if I replace C2 by this coefficient power 2, then the square length is given by this formula. We will need it for the sum of the squares, this square length of the projection. Now let's get a little bit close to what we need in linear modeling with respect to projections. We have another theorem. Suppose V is a vector space and D is any vector. Then D can be uniquely expressed as D plus C, D equal to C plus E. Once again, we want to solve this problem. And if we can construct a column space based on the columns of a specific matrix, which we get to that point, and find a projection matrix, then we can find a unique solution for that, because projection matrix solution is unique now. Okay, so we started with a vector space. Here C is in this vector space, and E is orthogonal to the vector space. If V is generated by the columns of A, then we can represent C as by this formula and E by this formula. We are getting a little bit close. If I compare this C with what I had at the beginning, you see we only don't have X here, so we are getting close to that. Now let's look at the proof and see how we can get C and E this way. Okay, for the proof, suppose that D is equal to C plus E. Once again, I'm using the first theorem. So I can decompose D to sum of two vectors, which one is the projection and the other one is the orthogonal vector. According to the assumption of the theorem, C is in V and E is orthogonal to V. So I can write D as A C1 plus E, and it comes from the previous theorem. Then I can write from this formula I can write A prime D. Instead of this hash here, I use the T for the transpose. A prime D equal to A prime A C1 plus A prime E. Since E is orthogonal to V, so I can find that this is equal to 0, and consequently A prime D is equal to A prime A C1. Once again, V is a column space of A. Since it's a column space of A, so A prime E is equal to 0, because E is orthogonal to V. From this equation, I can determine C1, and this is actually a consistent equation. If you know, we add this the right hand side to the left hand side matrix, then the rank of A prime A is equal to the rank of the embedded one. So I can better say augment. If I augment A prime D to A prime A, then the rank of the left hand side is equal to the rank of the right hand side. So the equation is consistent, and we can find a solution. We can find a solution for this system. Once again, in order to remember the consistency, meaning it means that we have a solution. We have a unique solution. Okay, let's go to the other page. In this case, C1 is given by A prime A generalized inverse A prime D, and this is the way that we can find. But for any generalized inverse of A prime A, therefore I can write C equal to A C1, and if I replace C1 from here, then C is equal to A prime A generalized inverse A prime D, and the first part is actually proved. And also we can find E, which is the difference D minus C, and we can then factorize D from right hand side and find this formula. So the theorem is proved. And the only thing that we need here is to use the generalized inverse to get C1, and because it's a consistent equation, I can write it as a prime A generalized inverse A prime D, and this way we can then find C, because actually C is given by AC1. So I'm connecting these two together, and we can find then D as AC1, which is A prime A generalized inverse A prime D, and simply E follows. Okay, now suppose that solution C1 exists for this equation, and let C equal to AC1 and E equal to D minus C. Then we can write D equal to C plus E, which C is in the vector space and E is orthogonal, because A prime E is equal to A prime D minus A prime C, which I can then replace C with AC1 and write it A prime D minus A prime AC1. And from the fact that A prime D is equal to A prime AC1, I can then write it as A prime AC1 minus A prime AC1 equal to 0. And then in this way, we can understand that it is then orthogonal, as we already had it. In order to show that it's a unique solution, we can construct, or better said, decompose D as sum of these two vectors, which E0 is orthogonal to V, the column space. Then simply writing A prime D, or better say, pre-multiplying D with A prime. We have A prime A C0, and then A prime E0, which is equal to 0, and we can write it as A prime AC1 according to the definition. So these are equal to each other. We can then write as A prime A C0 minus C1 equal to 0, and then the square of that, or even if you post multiply by pre-multiply by C0 C1 prime, then it is still equal to 0. But this equality is actually sum of the squares of the elements of this guard. So sum of squares of elements is equal to 0, which we can conclude that the elements are equal to 0. So we can assume that this is equal to 0, and from that we can then understand AC0 is equal to AC1, which shows the uniqueness for the first part. And if I replace it, we can then get E0, which is D minus AC0 here. I can then use this expression to find this equality, and then since AC0 is equal to AC1, we can write it D minus AC1, which according to the assumption or definition, it is equal to A, and we can then show that it's unique. So coming back to this expression here, if I use the first theorem, I can say this C is actually a projection. So and it's a projection of D. So I can use this to write this statement. The vector C is the projection of D on V. Now V is a space, it's a column space. It's a vector space generated by the columns. So now we are extending this projection to a space. So C is a projection of D on V, and E is a component of D, which is orthogonal to V. And this statement comes from the first theorem. Thus I can say that C equal to AC1. Once again, I'm using this projection term. So C, which is equal to AC1, is the projection of D. Now let's back to the equality that we had. If I have A prime AC1 equal to A prime D, I can say that this is the projection of D. Okay, but on V, on the space. So we can get the following conclusion. If I have such an equation, you are pretty familiar now with such an equation. If I write the common expression for that, which we have the linear equation y equal to x beta, then we can say, okay, we have x prime x beta equal to x prime y, and this way we are actually mimicking the same notation. So in this notation, I can then get the projection. So here we can also get the projection. Now let's back to this equation. If I have a equation something like that, then it implies that AX is the projection of Y. Just compare these two together. If you compare these two, we can say, okay, this part is the projection of the remaining. It is D, so it is a projection of Y onto the vector space. I show it by V. Vector space generated by the columns of A. Therefore, I can say AX, once again coming back to that, AX now is equal to A. I use the generalized inverse, is the projection of Y. And therefore, if I have such a expression, it is common to say that this is a projection matrix. So we can simply denote it by P. So in the equation of this form, the projection matrix is given by A prime A generalized inverse A prime. And so you will see, for instance, if I have beta hat, or better say x beta hat, then I can write it as a projection matrix with Y. So I can write the estimated values of Y based on the unique projection matrix multiplied by Y. So this is a very important conclusion, that whenever we have such a relation, we can find the projection of Y to the column to the vector space generated by the columns of the coefficient matrix, which is A here, and then we can define the projection matrix. Now, in what follows, I want to discuss about projection matrices. How can we construct projection matrices easily? How can we compute them? We're gonna consider some examples to discuss more about that. I'm gonna stop the video here to save the space and then continue with another video. Thank you.